best representation of the data? Probably not. But the values I'm estimating just by eyeball are, it has a mean of 50 and a spread of 35. So luckily, we have better things we can do than just eyeballing. And what we'd like to do is maybe think about the mean, estimating the mean of this distribution. What would be a good way to estimate the mean parameter of the distribution that generated this? What would you like your mean to, what would you like it, I mean, how would you like to, if you could score how good your guess is, how would you like to score how good your guess is?
100%.
What would 100% be?
Correct.
Well, but all I have is my data. So if all I have is my data, I don't know what the true value is. And the true value is not really a normal. But if I want to compare two estimates, and I say I want to compare 40 and I don't want to compare 80, 40 is probably going to be better than 80, but how would I know that? How would I know 40 is a better guess at the middle of that distribution than 80? What could I do to score that?
Is it a blind guess which you're doing, or is it like you're doing some sort of a, you see the largest and smallest when and guessing this can be the mean and. So, do you mean with this diagram how we can make it out it's better?
Let's say, well,
The more the
here's another guess.
no.
Is that as good?
No.
How do you know?
Because it's not near
Matching
central
spread.
tendency at all.
Yeah, it's not near the central tendency. So how might I give a score to that?
Just
How might I say that's a bad one? I'll keep this. That's better. That's pretty good. Oh, that's not quite as good. We're doing it by eyeball. What are you doing with your eyeball to judge that?
the black and the gray is how much they're coinciding, or there's less distance between them?
Yeah,
Better?
let's just focus on, don't focus on the spread right now. Focus on how well this line matches. In fact, let me get rid of the spread parameter for the moment.
Can you make it so the amount of points is equal?
So that would be one way to do it, and there are specific ways of estimating parameters that do exactly that, and they're actually called robust methods do things like that. They say, I want to pick, essentially what you're doing is you're picking the median. I want to pick the value that I miss half on one side and half on the other. That might not be the only or best way. What else could I do?
Why don't you just use the mean of your sample?
No, it may be skewed because the
Why would you want to do that?
outlines.
Because that's the best estimate
I'm
of the
not-
true.
Well, that might be the best estimate, but how do you know? We're defining what we mean by best estimate. So it might turn out that the mean is a good estimate of this, but I want to know how I can know that. How can I give the mean a score?
You can see if it follows a normal distribution, and if it does, then you can use that. Or if the distribution, like if the distributions match what you're trying, and then
I don't need to know anything about the distribution to come up with a best estimate of the middle though. So what we're doing here is thinking about what statisticians and mathematicians call a cost function. Okay. So what I want to do is think about how to score my guess at this function, my guess at the middle. And one way to do it would be to sort of try to find one where if I'm less than something, I give it a score of, if I'm less than a value, I give it a score of -1. If I'm greater than a value, I give it a score of +1. and I want that value to be 0. If I add those all up, I want it to be 0. So here I'm less. I give it -1, -1, -1, -1, +1, +1, +1, +1. I add those all up, my cost function will be 0. And if I take the absolute value of that, if I'm not in the middle, I'll have one point that's in the middle of them all, where my cost function will be 0. And every other point, the cost function will be greater than 0. That's not what we typically use, though. We typically use a cost function called squared error loss. Okay? So what I will typically do is take each point, compute the distance of each point to the mean, square it, and find the average of all of those.
Each point in the sense is split, the black points.
Each of the black, so for any estimate of the mean, I can compute squared error loss. I could say, if I was up here, I could take all 100 points and say, well, this one is, well, what I do is I take the difference from my estimate and then I square it. So by squaring it, it does two things. It makes positive and negative differences equivalent, and it also punishes you more for being further off. So there are some really important theorems that show squared error loss is good because it's concave, which means that it's you need a concave cost function in order to really pin down where your mean should be. You just have to worry that this is what we do, and practically it works. But for squared error loss, for these 100 points, I would calculate the difference between this and my estimated line. I would square it, then I would either add them all up or I would find the mean of them all. And that would be my measure of how good my estimate is.
This has to provide a more accurate estimate of best representation of the middle than looking at the shape of the distribution and calculating the different kinds of, like, average, median, like, different kinds of middles, right? Like, this provides a more accurate representation.
Well, so I haven't talked about how to estimate the middle yet. All I've talked about is a way of judging whether it's good. Okay. So.
So what you're doing is you just through an eyeball a mechanism, we just sort of ideating. The data is small, we can do that. But,
yeah, you will hopefully never have to do it by eyeball again. But I want you to, we're walking through this piece by piece because if you don't see it from this perspective, you're not going to understand why we do it the way we do it. So I could judge how good one of these are by computing squared error loss cost function. Okay, that's the next step.
So you're not just counting how many are above and how many below.
I
You're also
could.
weighting in the distance from
Yeah.
that.
Yeah,
That's
yeah,
what I
as well.
said, but this is the
that would be that's a different cost function than just counting.
So they're both cost functions.
Yeah, you can make a cost function be anything, if it's, but hopefully, it gives you some estimate of how good that middle. So the median one is actually it's becoming more and more popular to do things like that because it's more robust to weird data. But it's not. There are also problems with it, but it's becoming a popular alternative. Yeah. So, in fact, there was a psych review paper recently that did that. It was something really just a statistical method, and they got a psych review paper out of it about 4 years ago. So all I'm doing here is the same function, but I'm taking that middle estimate and I'm subtracting it from the data and I'm squaring it and finding the mean. So that's our definition, squared error loss, and I'm going to return that value so in theory I could use it, or I could record it or something. So now, but all I'm going to do is plot it. Okay, so now it looks, this is not going to care about my estimate of the variance yet. We're going to worry about that in a little bit. But here's my mean squared error, or my squared error loss cost function, when I use a mean of 41. Here's when I use a mean of 44. So it was 1114, 1101, that's better. The smaller the better. 48, 1111. So now I'm going in the other direction again. So maybe
So the spread has nothing. The spread is not involved at all. Correct?
Not in this-
Just the
not in
mean
this case.
estimate. Okay.
we may want to estimate the spread, but we don't have a way of doing that right now.
So that wouldn't change the number. This is strictly
Right.
your mean estimate.
All I'm doing is looking at how good
The mean
these estimated. Okay.
That is the distance from the point from the line. That's what we're looking at, isn't
It's the,
Yeah.
yeah. So this one produces,
Oh, plot mean two. It's plot mean two.
oh, okay. So even though I couldn't tell the difference by eyeballing, the difference between 40 and 50, it looks like 40, somewhere above 45 is actually good, best. There's a difference between 40 and 50, and it goes down between them, and there's a trough between them. So somewhere about 45 looks like it's maybe the best estimate. And this I can do by trial and error, but there are numerical methods that people use all the time to do this type of estimate for complicated distributions. I would never